Okay, let's dive into this. Our world is just full of randomness, right? Stock prices are all over the place. The weather seems to have a mind of its own. So how on earth do we make sense of, or even try to predict, things that seem totally unpredictable? Well, that is the fascinating challenge we are going to tackle today with something called stochastic processes.
So here's our game plan. First up, we'll get to the heart of what it even means to model randomness over time. Then we're going to uncover the two key dials you can turn to define any random process. Those dials combine to create 4 different realities, which we'll explore. We'll also look at a special process with a kind of amnesia. And finally, we'll bring it all home and see how this theory leads to real-world prediction.
All right, Section 1, Modeling Randomness Over Time. We're really starting with the biggest question of all. How in the world do you find a pattern when all you see is chaos? I mean, seriously, think about it for a second. The price of a stock at the end of the day, the number of claims an insurance company gets hit with, even just the daily temperature. They all change over time, and they all have this huge element of chance baked in. So the real question is, can we actually build a mathematical picture of that randomness?
And the answer is yes, with this surprisingly elegant tool called a stochastic process. Now, that sounds complicated, I know, but the core idea is pretty simple. If you think of a single random variable as one random event, a stochastic process is just a whole family of them, all lined up in order of time. It's like taking a series of random snapshots of a system as it evolves.
So how do we actually, build one of these processes? Well, it turns out you can think of it like you're in a control room, and you've got 2 main dials to play with. These 2 settings are the fundamental building blocks that define the nature of any process we want to model.
The first dial is what we call the state space. All that really means is it answers a simple question. What are the possible things we can observe? So in a life insurance model, for instance, the state space might be as simple as healthy, sick, dead. Those are the only options, the only states you can be in.
And dial number 2 is the time set. This one's all about the when. When are we actually looking at this thing? Are we checking in at specific separate moments, like a yearly checkup? Or could it change happen at literally any instant, any moment in time? Now here's where it gets really interesting. Both of these dials, the state space and the time set, can be one of 2 flavors. They can be discrete, which means the values are separate and distinct, like steps on a ladder. Or they can be continuous, meaning they can take on any value within a range, more like water flowing smoothly from a tap.
And this is where the magic happens, which brings us to Section 3. When you realize you have 2 dials, and each one can be set to either discrete or continuous, you suddenly have 4 fundamental combinations, 4 completely different kinds of realities that we can model.
And this table just lays it out perfectly. Let's start in the top left. You've got a discrete state at a discrete time. A great example is a car insurance discount. It can only be 0%, 25%, or 40%, and they only check it once a year. Now, move to the right. Discrete state, but continuous time. Think about someone's health status. It's either healthy, sick, or dead. Discrete states, but that change can happen at any moment. Bottom left. Continuous state, discrete time. That's like the stock market's closing price. The price itself can be almost any number, but we only record it at a specific time each day. And finally, bottom right, the whole shebang. Continuous state and continuous time. This is like cumulative insurance claims, where random amounts of money can come in at any random time.
So what does this actually look like when you graph it? Well, if we plot something like daily temperature, that's a continuous value we check at discrete times, we get a line graph that goes up and down. We connect the dots. But if we plot rainfall, which is just a simple yes or no, the graph just jumps between those 2 levels. It's flat, then it jumps. The way the graph looks tells you everything about the nature of the process.
Okay, now for something really cool, a fascinating little twist. It turns out some of these processes have a special quality, a kind of superpower that makes them way, way easier to work with. It's called the Markov property, and it's all about memory.
So here's the deal, and it's a huge one. For a Markov process, the future depends only on where you are right now, in the present. The entire path you took to get here is completely, totally irrelevant. It's like the process has total amnesia. A non-Markov process, on the other hand, is the opposite. Its future can be influenced by everything that's ever happened to it before.
To put that a bit more formally, the Markov property just means that to predict what's going to happen next, all you need to know is the state of things right now. The past offers no extra useful information. You can literally just forget about it. And that is the superpower. It lets you ignore this massive, tangled history, which makes these models so much simpler and faster to work with. It makes problems that would be computationally impossible suddenly solvable.
This example from the source material just nails it.
Think back to our healthy, sick, dead model. If we make an assumption that when a person recovers from being sick, they are fully healthy again, then their future health depends only on their current healthy state. The fact they were sick last year or last month, it doesn't matter anymore. That's the Markov property right there in a nutshell.
Okay, so we've got these incredible theoretical tools. We have our dials, we have our special memoryless property, but what's the payoff? Why does any of this really matter in the real world? In a word, prediction.
Let's build a super simple stock price model right now. We start at a price, say 100 pence. Each day, it randomly goes up or down by 1. Simple enough? But the key thing to see here is that the price on day 1 depends on where it started, and the price on day 2 depends on the price from day 1. Each step is linked to the one right before it, creating this chain of dependence that unfolds through time.
And this right here is the whole point. That chain of dependence we just saw, the fact that today is connected to yesterday and tomorrow is connected to today, that is the entire reason we can make predictions. It's what allows us to look at the past and say something, anything, meaningful about the future. Without that connection, the past would tell us absolutely nothing.
And believe me, this isn't just some academic exercise. These models are the engines running in the background of our world. They're used in finance for stock prices, in insurance for forecasting claims, in economics for analyzing data, in pensions, in science for simulating weather, you name it. They are everywhere.
So, we've seen how stochastic processes give us a language to describe and a lens to analyze all the random, messy, chaotic parts of our world. We've basically equipped ourselves with the tools to find the pattern hidden in all the noise. So the only question left to ask is, what unpredictable part of our world would you want to model first?